Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I am your guide, Dr. David Irvin, and we will start with Chapter 3, Part 1, Alkanes and Cycloalkanes. Okay, so we're starting to get into the actual structure of organic compounds. And so the first one we want to talk about is what we call a hydrocarbon. A hydrocarbon is organic molecules that contain carbon and hydrogen in them, okay? Specifically, hydrocarbons are those that contain only carbon and hydrogen in them. Once you start adding oxygen, that turns into another functional group. And so this is our most basic structure we have. We have different types of hydrocarbons. We have what we call a saturated hydrocarbon. What that means is every carbon only has single bonds. All the carbon-carbon have single bonds, and there's single bonds to all the hydrogens here, okay? When we have saturated hydrocarbons, that means every single carbon is sp3 hybridized, okay? So this general group of saturated hydrocarbons are called alkanes, okay? That means that we have all of these are saturated or sp3 hybridized carbons that are arranged in an open chain, okay? They would be called cycloalkanes if they formed any kind of ring, okay? So the alternative name is what we call aliphatic hydrocarbons. That means the same thing as a saturated hydrocarbon. Aliphatic implies that there are no double bonds in the organic compound. Okay, so if we look at the four classes of hydrocarbons here, we have what we can call saturated or unsaturated. Saturated are where all the carbons are sp3 hybridized and each of the carbons only has single bonds. Okay, the next thing we can have is what we call unsaturated, meaning that we have removed at least two hydrogens such that we have to form more than a single double bond between at least two of the carbons in the system. So if we had a single double bond anywhere in the system, we would have what we call an alkene, where we have at least one or more carbon-carbon double bonds. If we had one or more carbon-carbon triple bonds, those would be called alkynes, and those are sp hybridized carbons to do that. Okay, we can also have what are called arenes, which tend to be a certain type of double bonded carbons that are in rings that have certain laws that let it have different reactivity than other systems. We will be addressing all of these as the semester progresses. Okay, so for our aliphatic hydrocarbons, again, all the carbons are sp3 hybridized, therefore they all have a tetrahedral geometry. So if we were to draw it out in its extended form, it would look something like this zigzag pattern here. Does that mean that it's structurally rigid in that pattern? No. All of those bonds are free to move, but all of the bond angles still remain at about 109.5 degrees because they're all equivalent sp3 hybridized carbons. Okay, so when we do draw these things, we can draw them out as CH3, CH2, CH2. However, that gets a little hard. And so what we tend to do is we do what we call the line angle formula, which is an abbreviated way to draw this. So when we do this, what we're going to see is that each line represents a bond between two carbons, and the angle that it has is the angle between the carbons that are bonded to it. If there are no other things drawn on there, we assume that the hydrogens fill in the other bonds available to it. So if we were to look at a ball and stick here, we would have the line represent the carbon bonds here, and then the hydrogens would fill out the rest of the system, and they're understood in the line drawing. If we were to actually draw that out in what we call a condensed form, we would say it's CH3, CH2, CH3. Okay, again, that would be difficult to line. So the line formula we'll move to very quickly and use the line formula for almost all of our structures for later chapters, okay? So if we only have 3 carbons in it, we would have 3 carbons, 3 hydrogens at the end of each chain, and 2 hydrogens on each of the carbons in between. If we add a carbon here, that means we end up with 2 sets of the CH2s in here and a CH3 at each end. And then we can extend that chain as long as we want. And we have no branching. This is, again, the hydrocarbon chain, and this is what we call the line angle formula. Okay, so all the alkanes have the general formula of carbon, and we'll have 2 times the number of carbons plus 2 hydrogens. Okay, so what that means is that each carbon has a CH2 on it, and then the ones at the ends have 1 extra hydrogen each to terminate the end. So the general formula is carbon, however number of carbons you have, hydrogens 2 times that number of carbons plus 2. Okay, so if you see that generalized formula, you know it's a saturated alkane. Okay, so it's important that we learn the different names for the different groups. The first 3 are special, and then the rest follow the usual metric system of penta, hexa, hepta, octa. So we just have to remember that the 1 carbon is methane, 2 carbon is ethane, 3 carbon is propane, and 4 carbon is butane. After that, it follows the standard metric system. Okay, so now that we have hydrocarbons here, and the most basic hydrocarbons just have a carbon bonded to a carbon bonded to 1 other carbon, so that we have only carbon and hydrogen bonds. However, we have different isomers possible. For example, if we have 1, 2, 3, 4 carbons, and our structure has the fully saturated, makes it have 10 hydrogens, we can draw that in a number of different ways. In this first drawing here, we have it drawn such that there are all of the carbons make a single linear chain. And we call this the straight chain hydrocarbon, okay? However, if we just take this bond and break this bond and move it here and move the hydrogen that was attached over to the end here, we can have a different isomer. And this isomer has the exact same formula, but it is chemically different than the other form. This one right here is called butane, and it's a straight chain hydrocarbon, and it has a boiling point of just below 0 degrees C. However, if we move just that 1 methyl group and get a different constitutional isomer, meaning we attach the carbons in a different order, we actually get a lower boiling point. And it has a lower boiling point because it has a smaller surface area. And we'll talk about that in a little bit. Okay. So we can have a variety of different constitutional isomers having the exact same molecular formula, and they are different compounds and have different properties. Okay, so the number of different constitutional isomers goes up with the number of carbon atoms you have. Okay, so if you just have 1 carbon, you have 0 constitutional isomers because you have methane. It's 1 carbon with 4 hydrogens on it. Okay. However, once you go up to pentane, once you have 5 carbons, that allows us 3 different constitutional isomers available to us. And if we double that to go up to 10, we actually end up with 75 constitutional isomers available. And when we go to 15 carbons, that goes into 4,000. And by the time we get to 25 carbons, there's over 36 million different isomers available to it with just carbon and hydrogen. Okay, so the variety of these things is really, really high. So we need to have a systematic way of naming these things so we have an unambiguous way to say we have exactly this compound and this, everybody can draw it that way. And we'll get into the nomenclature of this in the next video. Okay, so one of the reasons we know these constitutional isomers have different are different is because they have different boiling points, okay? Once we start with very low molecular weights from 1 to 4 carbons here, most of these are gases at room temperature. So you think about methane and propane, which are in cylinders, butane lighters, that's just a little bit below boiling, a little bit below room temperature, but it's still a liquid if it's pressurized. So the fact that these are very low molecular weight and have very few interactions means they have very low boiling points. As we get to slightly higher molecular weights, we start seeing them as liquids, okay? This would be things like gasoline, kerosene, and hexanes that you would use to clean different automotive parts. Okay, once we get beyond that, things start getting waxier and solids. Okay, so once you start getting to paraffin and fats and oils, those tend to have more than 18 carbons and tend to start solidifying there. Now, if you go to very high molecular weights called polymers, which we'll talk about in chapter 16, the properties change again. Okay, now, even though these can have different constitutional isomers, the density of these materials is approximately around 0.7 grams per milliliter, which means both liquid and solid alkanes float on water. Okay, so that lower density comes from the fact that we have the tetrahedral shape that it's forming the two hydrogens up and the carbons down. That gives it a lot of volume and therefore a low density. Okay, so we talked about different constitutional isomers, and different constitutional isomers actually start with the basis of their properties is because of the number of carbons there are. However, their boiling points and melting points change with the number of different branches they have. And this can be seen here where all of these are different isomers of C6H14 right here. And what we see is that the straight chain, the longest chain itself, actually has the highest melting point and the highest boiling point, okay? And it has one of about an intermediate density here, okay? So if it's straight chain like that, it has the most interaction it can have with other molecules that it can have. That's what gives it its highest melting point and boiling point. As we start branching the system, the system gets more and more like a sphere. And so it has less and less surface area. That less surface area actually lowers the melting point and the boiling point of the material because there's fewer interactions with the molecules next to it. And we're going to talk about how different interactions affect boiling points and melting points as we change functional groups. So keep in mind that in these constitutional isomers, all we have are what we call dispersion forces or London forces. And that's a very weak force, and therefore they have very low boiling points. Okay, one of the few things that these things can do is that they can be oxidized or burned, okay? The carbon-hydrogen bond is a nonpolar bond. It's fairly strong, and therefore there's not a lot of chemistry that goes on with these materials, okay? So the primary type of reaction that these alkanes do would be combustion. We can take methane and hydrocarbon and oxygen and burn that, okay? And so we can actually think about the stability of a compound or the amount of energy in that compound by measuring the heat released when we burn something. And this is called the heat of combustion. This heat of combustion gives us some idea about the number of components in there or the total energy stored in that molecule. So if we think about this, if we burn methane, we only get about 886 kilojoules per mole when we burn this. However, if we burn propane, because again, we have 3 different carbons that have to be consumed here, we actually have more energy that gets released during that process. So if we have a burner that's designed for methane and we burn propane in it, it's going to burn hotter. Okay, so that's how we should think about heat of combustion. Okay. So where do these hydrocarbons come from? Most of the hydrocarbons here are actually dug out of the ground and are from oil and gas reserves. And so we have natural gas. Most natural gas is a little bit of ethane and mostly methane. In petroleum, we actually have a lot of the other like butane, etc. Then we have different boiling points above that. You can go for gasolines, kerosenes, fuel oils, lubricants, and asphalt. The other source of hydrocarbons we have is from coal. And in coal they tend to be higher molecular weights, and therefore they are still hydrocarbons. However, they are not liquids. They are in the solid form at room temperature. So one of the cool ways in which these things are actually isolated is you take crude oil and you put it in a steam boiler and heat it. up. And if you do this in the absence of oxygen, they will not burn. And so you can, by going up the tower, it gets cooler and cooler and cooler, and different things distill at different times. So if you have something and you inject it into the middle, the parts that boil at a certain level, for example here, things that boil at 350, the things that boil above that are actually down below here and are residues, and they don't continue up the column. The ones that everything else above that boils out of this, and that gets us to our lubricating oils, like the oil you put in your engine every 3,000 to 5,000 miles. That's where this fraction would be. The next one up would be what we call fuel oils. And fuel oils are things that you typically burn in a house, in a combustion type chamber to create steam or other things like that. The next thing up, this would also be in like diesel fuel would also be in this range here. The next level up is what we call kerosenes. Kerosenes and jet fuels are at that next higher boiling point up. They're harder to combust, but they have a higher energy density because of a higher number of carbons. The next fraction is gasoline. Then, of course, all the higher things like ethane, methane, and butane, etc., come out the top. Okay, so that concludes Chapter 3, Part 1, Alkanes and Cycloalkanes.